Good day, welcome to the second video on chapter 1.4. We're going to look more about lines. Now remember, what is a line? A line is an infinite set of points in R3, or it's a subset of R3, i.e. L is a subset of R3. Now there are two ways you can denote a line, either in set notation or as a vector equation, but do not confuse the two. So we can write the line is a set of vectors of the form TP plus 1 minus TQ, where T is a real number. Or we can say it is all the vectors that satisfies the following equation. X equals TP plus 1 minus TQ, where T is a real number. Guys, again, notice the notation. X, P, and Q are vectors, hence we're putting lines on top of those variables. Alright, so in the previous video, I left you with the following question. Given two lines in R3, two straight lines in R3, what possibilities exist for their intersection? So I hope you thought about it, alright? And there are three answers. So either you have the possibility that the lines intersect in a single point, and that is example 1.4.13 in the textbook. Another possibility is that the two lines do not have any points in common. So a fancy way of saying that is the intersection of line 1 intersect line 2 is the empty set. This is example 1.4.14. So if you haven't given it a go, please pause this video and do it now. The third possibility is that the two lines are actually identical. So the intersection of the two lines is either the first line or the second line. And if you want an example of that, do example 1.4.15 in the textbook, alright? It is important that you see actual examples of two lines intersecting in a single point, two lines do not have any points in common, or that two lines are identical, so that you know that this can occur. And this is the only possibilities that can occur. Alright, so my next question. What can we say if two lines intersect at more than one point? And can we prove it? Now, looking at the examples that I mentioned above, we can clearly see that if two lines intersect at more than one point, then the lines got to be identical. But can we prove it? All right. And you see, to be able to prove things in mathematics, you need definitions. All right. And this is why we defined what do we mean by a line as a set of points in R3. All right. So the question is, can you prove it? And this is the theorem. The theorem goes as follows. If two lines, L1 and L2, intersect at more than one point in 3D, then the lines are identical. All right. Now, I'm not going to do the proof. You can do it. So please read the proof carefully. Scrutinize each line. The proof is on page 24 and 25 in our textbook. All right. So this again shows us that the way we've defined lines agrees with our human intuition. So if you have two straight lines in 3D and they intersect in more than one point, then the lines are identical. Alright, so please give it a go. Now the next thing that we want to talk about is the idea about parallel lines. So we've already seen parallel lines in 2D, but now we are looking at straight lines in 3D. So we want to know, can we define what does it mean for two lines to be parallel in 3D? And the answer is yes, we can. And here's the definition. So let's take two lines. So line 1 is of the form Q plus TP minus Q, where T is a real number. And line 2 is a different line. So line 2 is B plus TA minus B, where T is a real number. So here you have two lines in R3. Now we say that the two lines are parallel if and only if we take this vector B minus Q, and then we take this vector A minus B, and we say the vector of the first line P minus Q equals alpha times A minus B for some non-zero real number alpha. So this is what we mean when we say line 1, find the correct vector, in this case P minus Q, is a scalar multiple of A minus B coming from line 2. Alright, now just as a quick remark, so we see that line 1 is parallel to line 2 if and only if P minus Q equals alpha times A minus B, where alpha is a non-zero real number. Now, because alpha is a non-zero real number, we can divide both sides by alpha, and we can rewrite this as saying 1 over alpha times b minus q is equal to a minus b. And because alpha is a non-zero real number, 1 over alpha is a non-zero real number. And if we replace 1 over alpha with beta, then we get beta times p minus q is equal to a minus b, where beta is a non-zero real number. And we can rewrite this. This happens if and only if a minus b is beta times p minus q. So what we actually see is the vector in front of the parameter of line 1 and the vector in front of the parameter of line 2, that these two vectors are non-zero scalar multiples of one another, and the order doesn't matter. And this is why this remark is so important. So the order in which you calculate the vectors from the one line and the other line doesn't matter, as long as the correct vector in the first line is a non-zero scalar multiple of the vector in the second line. All right. Now, is this a good definition? And then the answer is yes, and this is shown in Theorem 1.4.19. If line 1 and line 2 are distinct, so different, so there's at least a point on the one line that's not on the other line, parallel lines in R3, then they do not intersect. Now, I'm not going to do the proof. I'm just going to sketch an outline of the proof. So remember, a good thing with the proof is to start with a setup. So let line 1 be all of the points q plus t, p minus q, where t is a real number. So line 1 passes through points p and q. And let line 2 be a line through points b and a. So line 2 is of the form b plus s, a minus b, where s is a real number. Now, two different lines, it's useful to use two different parameters. Be distinct lines in R3. Now, you can say q is not sitting on line 2. I'm going to leave it for you why this is so. And then because q is not on line 2, we can then say q is not of the form b plus s, a minus b for any real number s. Now, because the two lines are parallel, from the definition of being parallel, it means there exists a non-zero scalar alpha such that p minus q is equal to alpha times a minus b. Now, we can manipulate this, and we can then say that that means that line 1 is a set of points of the form q plus alpha t times a minus b, where t is a real number. So why it's true, I'm going to leave it for you to verify. All right. Now, assume that the two lines intersect at least once for a contradiction. So at the heart of the proof, it is a proof by contradiction. So if the two lines have at least one point in common, give that point a name. Let's call it point x, vector x. So vector x is sitting in the intersection of line 1 and line 2. Now, can you reach a contradiction? If you get stuck, have a look at exercise 1.4, number 13. Because we reach a contradiction, it means that the assumption that the two lines have at least one point in common is false. What does it mean? It means that the two lines do not intersect. So the intersection of the two lines is the empty set. All right. But now for a fun question. Is the converse true? So that means if two lines do not intersect, does it mean they have to be parallel? And the answer to this question is not in 3D. Now, to be sure why this is not always true, you need to provide an example. So if somebody gives you a statement and it is not always true, you disprove it by an actual example. All right? So proof is a long argument using mathematical logic, but if something is false, you just have to give one instance where it fails. And here is an example where it fails. Let line 1 be the 3D vectors of the form 1 minus t, 1 minus t, 2t, where t is a real number. And let line 2 be the 3D vectors of the form s to s minus 1, where s is a real number. And let's start with part A by showing that the two lines are not parallel. All right. Now, in the current form, it's not so easy to see that they are parallel or not parallel. All right. So let's start off by saying, okay, line 1 equals, and now let's rewrite this 3D vector. So we take out the constants, which is 1, 1, 0, and then we're left with minus t, 2t, where t is a real number. And then I can rewrite this as 1, 1, 0. And I can take out t, and I'm left with minus 1, 2, where t is a real number. So we have line 1 in a nicer form, because we know if we want to check if two lines are parallel, we need the vector in front of the parameter, in this case parameter t. All right. Now likewise, line 2, I can rewrite in a nicer form. So looking at the constants, it's 0 to minus 1 plus s. The coefficients of s is 1, 0, 1, where s is a real number. So I'm busy doing A. So the given format of line 1 and line 2 is not nice, so I quickly rewrite it in this form. So I know I'm going to use that vector, and I'm going to use this vector. So I'm going to use a proof by contradiction. So I'm going to say, if line 1 is parallel to line 2, then there exists an alpha which is a non-zero real number such that this vector, which is minus 1, 1, 2, is equal to alpha times 1, 0, 1. Because this is a definition. If the two lines are parallel, this had to be true. And so this vector is minus 1, 1, 2. And this becomes alpha times 1, alpha times 0, alpha times 1, which becomes alpha 0 alpha. All right? And now looking at the, I'm sure you can tell me what it is, the second component we get. So the second component here is minus 1, and the second component here is 0. So remember, if two vectors are equal, the first, second, and third components have to be identical. But this is false. This is false. So our assumption that line 1 is parallel to line 2, let me just write this a little neater. So line 1 is parallel to line 2 is false. Hence, lines are not parallel. So do you see how useful a proof by contradiction is? All right, we assume the lines are parallel. So we got that a certain equation must be true. This leads to a contradiction. And from the contradiction, we can see that our assumption that the lines are parallel is false. Therefore, the opposite is true. What is the opposite? It means that the lines are not parallel. All right. So if this is something that's new to you, please redo this question so you're comfortable with it. All right. And number B, to show that the question is, show that the lines do not intersect. So it is actually exercise 1.4.14 to show that line 1 and line 2 do not have any points in common. All right. So please do it if you haven't. So again, it is 3/4 to a page calculation to show that the lines do not intersect. So there's no point common to both lines. All right. So please make sure that you can do it and write out a nice little argument why the two lines do not intersect. All right. So some remarks. So we know in 2D, if two lines do not intersect, they must be parallel. But this example that I showed you was an example of two lines that didn't intersect, but they weren't parallel either. So it means that this is a property that's true in 2D, but it's not true in 3D. All right. So as a little bit of caution, it shows you that high dimension mathematics can be tricky, but it can also be lots of fun. All right. So here we have a property that is true in 2D, but not true in 3D. All right. So our study of lines and parallel lines is quite important because we see new things happening when we're looking at lines in 3D compared to lines in 2D. All right. Now, we can have heaps of fun with lines, but there are also other objects we can look at. All right. And as you can see from this picture, this is a sphere. All right. So what about spheres in 3D? All right. Now, for a circle, you need a center and a radius. For a sphere, you need the same things. You need a center, which is a 3D vector, and you need a radius r, which is a positive real number. And then you can define the sphere to be all the 3D vectors x, so that the distance from point x to the center is constant, and that constant is the radius of the sphere. So you can write this beautifully in set notation. S is all the 3D vectors x such that we want the distance from these 2 points to be r, and we know distance mean norm. So we want the norm of vector x minus vector c, the norm of that vector, to be r. And this, ladies and gentlemen, will define a sphere S. All right? Now, I'm not going to do examples of spheres. If you want to play with spheres, please look at our textbook. So there's a problem in example 1.426, another one in example 1.427, and another one in example 1.428, if you want to play a little bit with spheres. But this is the end of the video. I hope you enjoyed the video, and more videos are on its way. Have a nice day. Bye.